Chapter 16 is conjugation, resonance, and dienes. And we'll start off with a definition. Conjugation is whenever p orbitals overlap on 3 or more adjacent atoms. So we're going to look at some examples of conjugation, what you might be seeing. So let's look at 1,3 dienes. 1,3 dienes are going to be an example of conjugation. Oftentimes also we'll call these conjugated dienes. I'll try to show you what it means by that they're conjugated and how you can tell that they're conjugated. So there's your diene, and if you want to look at the orbitals, since in the definition it's overlap of p orbitals. So I've got a p orbital here, because there's a pi bond, there are an overlapping p orbitals on each of those first 2 atoms, and there's p orbitals on each of these 2 carbons. We should also place the electrons in each orbital, so each of these has 1 electron in it. So that makes this first bond. And the electron in each one of these makes the second pi bond. So if I look at this electron density, the electron density is delocalized across the whole system, of course then lowering the energy. So I want to contrast that to an isolated diene. Something like this. And if I'm going to draw the orbitals here and put in the electrons just like I did before, what you find is that in the middle you have this sp3 hybridized carbon that does not have a p orbital. And since it doesn't have a p orbital, this set of pi electrons and this set of pi electrons are isolated from one another. So the electron density cannot be delocalized across this whole area. Each one of these is isolated to its individual location. So there's no chance for delocalization because of that, because the electrons can't jump across the sp3 carbon. The p orbitals have to be continuous for conjugation to occur. So this is one example, a conjugated diene or a 1,3 diene. So in the next example, let's look at allylic carbocations. Remember, the allyl position is the position next to the alkene. So these are vinyl positions here on the alkene itself. Next to that would be allyl. So if I have a carbocation at allyl, let's draw the orbital picture to see what that looks like. So if I look at the p orbitals, each one of these has an electron in it. That's your bond. And if you remember, with a carbocation is trigonal planar with an empty p orbital. That's the shape of a carbocation. So what we have is we have 3 adjacent p orbitals that overlap. And so this electron density is shared along all 3. So this is only one way that you can draw your allyl carbocation. You could also draw it with an electron in the middle and an electron far to the right. Now, if we were going to take this structure and redraw what our alkene looks like, we would draw it like this, with the cation on the opposite side and the alkene on the opposite side. Now, what you remember from resonance, it's not these 2 going back and forth, it's actually some combination of both of these at the same time. So if you wanted the best picture that you could draw of what this allyl carbocation looks like, you'd say, well, there's a double bond in here somewhere, and there's a positive charge in there somewhere. That's the hybrid picture of the 2 resonance structures. Hopefully you remember from before that when we looked at stability of carbocations, that a tertiary carbocation is more stable than a secondary carbocation, is more stable than a primary carbocation. Okay, so now we want to place allyl in here. Okay, and if you remember, resonance always lowers the energy. So an allyl carbocation is even better than a tertiary or secondary or primary because of the resonance. And with the allyl, if you look at it, you might be tempted to look at this and say, this looks like a primary carbocation because the positive charge is on a primary carbon. But because of the resonance delocalization that's happening here with that pi bond, it's not considered primary at all. It's much, much more stable. In fact, it's much more stable even than a tertiary carbocation.